it's not the entire plenary, so that's actually a good sign too, right? Yeah.
I don't see short.
If they show up on the slide, they get close to credit. Okay, so if they show up on the slides, I think after that, we submit the slides and it's not.
Well, no, I was just thinking that. I don't think I have enough. I'm not going to say.
Beyond the slides, they take over as the last questions.
Okay, let's see both of these. You want this around this way and then tell me where you have to walk through it? Because I don't know you got running, right?
Yeah, I don't
So I can do that in 2 days.
So,
Hello. No one pays attention to me ever. So we're going to start in a couple of minutes. We have a contest of who can say that better. How many ways can you say that? I'm not even going to try and say it. We got Lego. Yeah. You can still talk for another minute. Then.
And if this turns out to be we got Lego, blame Barry Leva. I put the slide up talking to him about it, and he said he pronounced it that way within seconds. He has a gift, man. The guy has a gift. I'm shutting my control issues by the minute, so. Okay, we're going to go ahead and get started. Welcome you to the Technology Deep Dive on spherical routers, forwarding plane realities and implications for protocol designers. And we're, at least for now, working on whether we have REST consensus to pronounce it as we got Lego. I'm Spencer Dawkins. This is the lovely Alvaro and the lovely Karen to my left. And we will be your hosts for the next, hour and 55 minutes or something like that? You all want to say hi?
Well, I already said hi and everyone shut up, so I'm not going to say more.
I'll say hello as well.
And so this is a IETF activity, so we put up the Note Well slide and trust that people have read it and that they will make good choices. So we have, this is our agenda, and bashing it is okay. Just to do administrivia, like we said. So the pronunciation is we got Lego for until we come up with a better one. It stands for we got the last good one because Warren said all the good ones are taken when Cindy asked him for an acronym. And I said, oh no, we got the last good one. It's going to be like this the whole afternoon, guys. Plan to have fun. So we did the Note Well. We're willing to bash the agenda and want to talk for a few minutes about what we do at a technology deep dive. I'm going to talk for a few minutes about spherical routers. Smart people about forwarding plane realities are going to talk about forwarding plane realities. That'd be Frank, John, and Torles. We're going to be summarizing implications for protocol designers, and this is the part that I want everybody to go into this with the right mindset. This is a working session. It's not a tutorial. It's a working session. So we hope to all come out of here smarter than we came in, not just some of us. And we want to talk a little bit about the next steps for the summary of implications for this topic, and we want to talk about next steps for technology deep dives on other topics, and we'll be bringing up our sponsoring area director, the lovely Warren, for that. The We Got Lego, Etherpad, and Jabber Room are in the usual places, and you can find those most easily probably from the IETF agenda in the data tracker for links. Where are we? Yeah. It's okay. I should do this from over here. So when we started talking about doing this, we were saying first assume a spherical router with its zero gravity and 0 degrees temperature. So this is basically the simplifying assumptions that people make that help them do math. We've had spherical cows at the IETF for a very long time. This is actually Heather's company and group. You can see the spherical cow on her business card saying moo. But this is now spherical routers. Some routers really are spherical. Dingley made one, at least one. And if you're going to be encountering spherical routers in everything that you do on the internet, your problems are solved and you can go have more unstructured time. But if yours isn't, we're hoping that what we do today may be of use to you. So how we got here in the first place. So John Scudder gave a well-received talk on modern router design at the Internet Engineering Planning Group to a small audience in 2015. On Sunday mornings is when that group meets. And the other thing that's been going on is people assuming a spherical router. We say they exist, but most routers aren't spherical. And what that really means is that too many working groups encounter contentious cross-area or late IETF last call issues. Most recently, if you've been involved in last call and balloting discussions about a draft that was using IPv6 extension headers in a kind of an interesting way, but there's others. And these are late surprises for too many working groups, so we were hoping to do better. Warren and I thought a technology deep dive might be useful. Like I said, not a tutorial. People understand how routers work in general. What we're talking about is a cross-area working session on a complex topic. So we started recruiting people to help with a deep dive on modern router design, and that morphed, of course, it always does at the IETF, and here we are now. For what we're hoping for at technology deep dives, we need to complain about unstructured time. The working group chairs complained about unstructured time during the working group chair session on Tuesday. The community will complain to the ISG about unstructured time at the Wednesday plenary open mic in just a couple of hours, and you are here somewhere in the middle. So I would encourage you to aim those comments where they are most likely to be received well. So if we're not doing a tutorial, what are we doing? And we are doing, and Warren made me use the word information sharing, but he was the one that actually said, oh great, corp speak, on a complex cross-area topic, to have open discussions, to understand the world from each other's viewpoints, and to clear the air about some things that a lot of people may be confused about, and not particularly from one community. Together, this is the part where you're doing work, figure out what the implications are for protocol designers. Together, figure out what, if anything, we should do as a follow-on to the activity that we're going to be doing for the next little bit here. This is the classic picture of what I think we're talking about, where a bunch of blindfolded people are grabbing pieces of an elephant, and they know very clearly what they've got a hold of, but they don't know that they've got a hold of an elephant. And like I say, this is the classic picture, and it kind of does a better description of what we're talking about here than I could possibly do in words. I think we are to the forwarding plane realities, and would invite Frank, John, and Torlis to come on up and take the field, if that's okay. And thank you all for serving the community in this way. Do the right thing, whatever that is.
Let's say first, push the zoomy button so that we can forward slides.
You guys, we're not putting a talking a lot at this point.
Okay.
Okay, cool.
Am I starting this madhouse?
Only if you're sitting in front of the microphone.
But apparently, I walked up too fast, so I get to be the stucky. So this used to have a more grandiose title. Sorry, better? Thank you.
All the great ones are too tall in this thing.
That's true. I'm the shortest of us, so yeah, good. I know you would. All right. So those of you who looked at your agendas early in the week might have made the mistake of coming in here thinking that we were going to talk about, some kind of vision for the future and, what routers for the 22nd century are going to be. And actually, because I think the title was Modern Router Architectures or something like that. But it turns out that title was more in the sense of my undergraduate class on modern literature, which meant 19th century literature. So what this is really like is really about is what routers are when they aren't general purpose computers. So if that's not what you were here for, you can quietly make your way to the back now, and if you don't, then I'll assume that this is what you're here for. This sort of came out of that IEPG deck that I gave 5 years ago, sort of updated by the three of us, and I think a lot of it turned out to still be relevant to today, but you'll see seams in places, and that's because, of course, it's a design by committee. So we, start out by talking a little bit about what's a taxonomy of how we build routers. Oh, and one sort of disclaimer I want to throw in right at the beginning. And by the way, if you guys, you got a mic too, so interrupt me whenever. But at various points in the deck, I think we talk about things like, high performance routers, large routers, and so on. It turns out that most routers now are high performance routers, according to this definition, because of economic realities and that kind of thing. We dive into focusing on one particular flavor of forwarding architecture, which is a very relevant flavor of forwarding architecture, and end up kind of spitballing on what are some things that protocol designers should know and at various points in the past evidently haven't. Oh, and I should also add one more thing, which is that I do not design chips. I am a software guy. And you can think of me as like a sock puppet operated by a remote guy who actually does design chips and helped craft the original slide deck, and his name is in the fine print there. It's only in fine print because we took his deck and butchered it. But and I'm sure there are people in this room right now who know more about designing router hardware than I do, and I hope that you'll come up to the mic at will. And I think we're, there's no request to hold questions for the end necessarily. We're big boys, and if you bring up a topic and we want you to hold it for later, we'll ask you to. But otherwise, please, if we can have it be interactive, that would be nice. So we all know this, we've all heard this, but it only applies, good, fast, cheap, pick two. It only applies on my stuff, right? On your stuff, I want you to have all of it. And this is, kind of if we can come away with just one understanding from the next hour or whatever it is, it's that, this applies to your router hardware also.
So, we have camera. Okay, there is an X. So I wanted to maybe start before getting into the details we want to talk about for most of the presentation, to give a little bit an overview of what we may consider to be the landscape of the different realities of router platforms that we have today. Primarily also to make sure that it's understood that we can't talk about everything. So if we start in this picture, traditionally, the original routers maybe in the 70s or so were starting to be just general purpose CPUs. That has survived over the decades, has expanded itself very much. Maybe starting in the 90s by, having additional CPUs, not only one CPU that does everything, you design your next generation network service, let's call it multicast on a Sun workstation, the beginning of the 90s, but you basically started to have CPUs that were doing forwarding plane separately from those doing control plane, and then every line card getting CPU, right? So CPU was staying there. Then, later on it became less favorable, and, in the last 10 years, I think we've seen a lot of revival of CPU forwarding through a lot of x86, virtualization, NFV in data centers associated with a lot of even open source packages that allow you to accelerate this and leverage, the capabilities of them. These systems have a lot of interesting properties. Primarily, they're normally an ideal world for protocol designers because they're pretty much, the more general they are, the less, constraints you have by, they have different line cards and so on. They become fairly spherical, and that's very often what in the past protocol designers expected all routers to be. And obviously, the more you look through the landscape, the less that's true. The main issue, I think, for them is you have all the flexibility, but you have really no way to predict performance. So whenever we've been trying to, predict for a particular deployment, the performance of a combination of all type of features in the forwarding plane, well, you just got to measure it, right, because it's so flexible. Specifically for the IETF, I think what's interesting is that in the low end, like let's say in the IoT space, CPU forwarding routers are pretty much the only game in town. 8-bit, 16-bit, 32-bit CPUs, that's kind of the range to which they go. Embedded devices, small memory routers. There are a lot of IETF working groups that work with routers in that space, and also because they have the flexibility of this almost spherical router there, they basically can design protocol solutions that we have really a hard time, to scale up to higher platforms. So my typical example is the wonderful source routing header that was done in the role working group for Ripple low end. Took us a long time to get to that point as well. Let's say with SR v6 in, higher end routers. And that's because, CPU, a lot more flexible, faster to get to the protocol stage that you want. So then actually, the next step that happened in the 90s was really hardware switching, the most cost optimized, chips that you can build for a purpose, no flexibility, but rather you put the RFP that says it must do this protocol, let's call it IPv4, Ethernet switching. Please basically for the following speed build me a chip that is as cheap as possible. Obviously, that's a very good reason to not have flexibility. And in many networks, right, you basically design upfront mission specific networks and, never going to be extended, never going to change. Control plane, very simple. And that's basically been, still true until today. I think that's not going to go away. And I think that part of the equation is still the most difficult one for us in the IETF to build new protocols for. Primarily, it's a matter of, business case, right? If basically what you're trying to achieve and solve as a use case with your new solution in the IETF is if it's big enough, somebody will build you a dedicated device to do this. Example of this, actually, IEEE and friends, kind of these, layer 2 type of standards bodies, they're much more centric to that approach insofar as that when they're designing protocols, they very much have exactly that centric type of switches, mostly, even if it's a router, in mind, and they basically, in many cases, build dedicated ASICs for that, right? If you need some form of flexibility, maybe you add an FPGA that gives you some degree of, programmability, but that's very hard to extend and only done in exception cases. But so that's basically the opposite end of the spectrum. And then basically we have what we want to concentrate on for today's session, and that's what, as the common term, maybe multi-stage programmable forwarding. There are a lot of varieties. That's what John and us are going to talk more about for the rest of the presentation. That basically, from very long instruction word to basically, execution elements that almost look like small CPUs, over to a lot of hardware acceleration coupled with them. And that's the type of hardware that we're seeing now all the way through the network, distribution core, data center. Lot of differences in the different spaces still, right? Because these market segments are all large enough to validate, individual chip designs. We'll see how that is more going forward in the future. One, I think, very interesting aspect that came out of the data center was kind of the idea to make the consumption model of the chip and the forwarding plane somewhat more open, right? Because if you look at it, CPU forwarding, yes, everybody could program routing and is still programming routing on CPUs. Almost nobody can do that, on the fixed forwarding ASICs in layer 2 or layer 3 switching on the right-hand side. And in the middle, it's also very hard, been traditionally, to get access to any type of programmability of the forwarding plane other than maybe, establishing 5-tuple forwarding entries as the best thing of something like OpenFloor. So, but that's not what I would consider programmability. And so the question was always, how can people outside of the core vendors get into programming of these multi-stage programming forwarding entries? And so P4 was one of those, today probably as a programming most successful ways to attempt opening up that programming to other players. I think it has certainly been very successful in the research world because, a lot of researchers have started that are doing, networking to consider, trying to prototype their forwarding plane also in P4 and therefore be more exposed to the limitations of what an actual forwarding plane has. Not ideally, but a lot better as if you were just starting to build forwarding plane, let's say for Linux kernel or something like that, or DPDK, right? So that's basically, I think, a very interesting aspect for the future. Maybe even when you're doing things on the protocol side that's associated with certain things in the forwarding plane, how do you want to prototype that forwarding plane if you're not one of the vendors? So what else do we have there in this bucket? So beside what all the existing details that we're doing, I think at the end of the presentation, I'm going to talk a little bit more about that. I think in this space there is a lot of good work that could be done for more intelligent forwarding planes, and I think two of these areas that are very important in my opinion, but that are even at the edge of what the forwarding plane NPU could do is programmable QS. I think that's very hard. And then the telemetry as well that Frank has done a lot for. And in general, chip building has become a lot easier in the last 10 years, right? So, I mean, if you just look at the total number of startups that are building dedicated chips, and they're throwing just all the possible execution elements together, right? Whether it is, let's put some CPU cores, some, accelerators, some NPUs, some, AI is also important. Let's put an inference accelerator to do some more logic in there, DSP to even do more statistics for IOM and what you have. And so I think it's very hard to predict in which market segment we're going to see which evolution of, the current forwarding scheme. So always keep eyes open. So then the other part that I wanted to mention is that beside the forwarding plane that we're going to talk for the rest of the presentation about, there also is the poor forward, the poor control plane, right? So I wanted to call this the reference router from hell and everything you could do wrong on this space here, but I'm a little bit too afraid to write that down. But I think most people will understand high level. You have your control plane and you have your memory in there. There's some CPUs there. Then you basically have these magic forwarding chips that are doing things, and they'll also have a lot of or maybe not, memory, TCAM entry, on and off chip. That's going to be talked about in the presentation a lot more. But a lot of my experience in the past with protocol designs weren't necessarily only we just designed the next forwarding chip. What did you want to do? Oh, no, sorry, you just came 2 weeks too late. Please wait another 4 years for the next chip revision we're doing. I'm talking purely about the thing like, we only had 5 watts left in our 1 kilowatt box, so the CPU is going to be extremely slow. And by the way, it's going to be 8 cores, so if you haven't multi-threaded it, it's only going to be an eighth of the performance that you get in your control plane CPU. But don't worry that you can't calculate routing tables fast enough, because you won't be able to install them fast into the router, right? Because we've basically used the serial port down into the forwarding plane, and by the way, it has 10 line cards, so if you want to send to 10 line cards, it's even 10 times slower, right? So the router from hell. Obviously, I haven't luckily found a single router that has all of these problems, but trust me, each of, not a serial port, admittedly, but something similarly slow. So that's the problem overall, right? That basically trying to, for example, have more money in a router spent on the control plane when you build the box is something very hard to argue, because at the gist of it, the real metrics, and I had that on the previous slide, is really what data plane throughput do you need, and then basically, how much does it cost per bit as far as buying the box, the size of the box, and how much power goes through the box, right? And so that's why always in the majority of box designs, the poor control plane part of the solution is way on the back end burner, and in many cases it might actually better to start buying routers that don't have the control plane and basically connect a fast PC with a 100 gigabit port to it and use that as a high performing control plane router, just from past experiences. So was there anything else I wanted to say from this? I think this was good enough, so let me pass back here to John.
So now I'll say all the same things, only I'll say them way slower and with more slides. Exactly. So yeah, Torles just showed his router from hell, and that's pretty much the reference model. And again, everybody builds routers with more or less the same functional blocks. You've got, a functional block for your control plane. You've got to have a way to get the packets from the gazettas and get them over to the gazoutas, and that's your fabric. And, sometimes it's a real fabric and sometimes it's shared memory, but there has to be some way to move the packets around. And then, there's the packet forwarding logic itself. So, call it a packet forwarding engine or whatever you like, which is actually the thing that does the lookups, does the queuing, does the buffering, and so on. And it as we already, led with it, that sort of spans the whole range of flexibility from completely programmable to completely set in silicon. A slightly different picture of the same thing, and I think the thing to emphasize here is that you've got all the functions in the box, which makes it kind of attractive to think, oh, okay, look, I've got a nice general purpose CPU over there on the left, and I've even got another one over there on the right, and so I can really do everything. And it's true, you really can do everything as long as you don't mind taking, something like a 2 order of magnitude hit in performance every time you cross one of those domain boundaries, or maybe worse. I don't think I'm going to say a whole lot about fabric-based architectures. There's an interconnect. So, yeah, packet forwarding engines, like I said, are the things that do the work to figure out what to do with your packets, right? They analyze the packet, they do the lookups, they take care of the buffering, they take care of the simple or complicated queuing that you want to do, and they again, the programming model can run the gamut. And really, a lot of what's coming up here is there is no new thing under the sun. We only know a certain number of ways to build computers and a certain number of ways to make them fast. And, it's sort of clocks, cores, how fast you get to your memory, and you only have a certain amount of space on your die. And I guess final bullet, right? I'm not going to focus. We're not going to focus on like, is this all one chip? Is this multiple chips? Again, this is sort of general computer system design and not unique to routers. It's attractive for all kinds of reasons to put everything on one chip if you can, and sometimes you can and sometimes you can't. So there's our cartoony reference model of what these things are. Same thing, put on 2 axes, also cartoon axes, not to scale, where your general purpose compute engine is, all the way off the top on flexibility, but it's, jack of all trades, master of none. And by the way, why did you want a floating point unit in your router anyway? Why are you buying those gates and probably never using them? And, all the way over on the other side is, the thing that's completely set in silicon, or, more likely is the multi-stage thing that's somewhat programmable, but the stages are, really separate hardware units, and God help you if you forget that. No, that's still me. Okay. Right. We've resorted these several times. So, right. So I think the first bullet has been sufficiently belabored. But so what are the kinds of trade-offs that we're making when we put these things together? This is an example trade-off, but it in my mind anyway is maybe the most critical one, because it's a thing that gets baked in, and then you really can't change it once you've taped out the router. And then if you, and this will be repeated with more pictures in a few slides, but typically when you're forwarding a packet, you've got some number of bytes of key data that go up towards the forwarding chip, and everything else that was in the packet ends up in RAM, and it's really, really expensive to get to in terms of clocks on that forwarding chip, if you can get to it at all. And of course, as with all system designs, the trick is to be as inflexible as you can while still being able to do everything you have to do. And the problem is that when you're building hardware, if you guess wrong, your guesses last a long time. I'm sure there are people in this room that can, tell us horror stories about, just how old the oldest router in their network is. It's probably very old. Because routers, the high-end router of today gets moved into the, some other application tomorrow, and they just keep living and living. So why do that? Torla spoke to that earlier. Because of power efficiency. Because of volumetric efficiency, the 500 million to a billion is probably low now. This was originally presented 4 years ago and that number hasn't been updated. But the sort of 2 orders of magnitude thing I alluded to earlier is probably still about right. Okay, why care? And that gets back to the what motivated this BOF to begin with. Well, just because of the economics of building these things, these architectures are, not only in use, they're, from my keyhole at least, their use is becoming more, not less, ubiquitous. Because you can buy a, $200 box or whatever that has quite a capable forwarding chip in it, but it's the reason it's capable is exactly because it's not a, it's making the trade-off of getting higher density or more forwarding speed at the cost of being less flexible and less programmable. And experience has demonstrated that certain protocol characteristics, even though they look great on a whiteboard and look even great in a C compiler and look great when you're running a prototype on a virtual machine, they don't look so great at all running on a forwarding chip.
All right, I think I'd like to go and baseline the thing even a little further. So some really motherhood and apple pie trade-offs. So we have a piece of real estate. That's our chip, right, our die. And it is up to us how we want to go and utilize that piece of real estate. So you have a set of gates. You can use these gates to do forwarding. You can use these gates to count what you're doing. You can use these gates to store stuff. But you can't use one gate for all of that. So we have to go and choose. And you can say, well, I want more. That means you need to go and grow your real estate. But if you grow your real estate, you increase yield because, well, there is a waiver and there's defects on the waiver. So that drives costs like crazy, which is why chips have a certain size. And one of the fundamental things that, well, we need to go and care about is power, right? And you can say, well, there is dynamic power, and dynamic power is the product of, say, frequency, capacitation, and, well, voltage to the square, plus some activation, or times some activation factor. That's the dynamic part of that. But as we kind of started to hit the limits of Dennard scaling, that also meant people started to go and package things. So you can't shrink the gate anymore. So you started to go and pile things on top of each other. And you're just going denser. And that means also that static power is a significant concern these days, right? So the denser we pack, the more static power, i.e. leakage we have that we have to go and deal with. And that's just the chip. The stuff that you push into the system also needs to go out of the system again, and that is cooling. And I remember one of our routers a little while back, I think we spent more power on the fans than on actually driving bits in the system, just because we had to bend the air 3 times as it passed through the system. Now that you have the air outside the system, you need to go, well, cool it down again. And that's okay if you may have a single router. It's not so okay if you have many routers in a relatively constrained environment, like if you're a data center. So again, something to take care of, unless we always want to go and put a power plant next to a data center, which is what people do, right? So If I'm a data center person, my design constraints from an optimization perspective will be very different than I'm just operating one core router at one place, despite the fact that I have this recurring cost of power that I need to spend anyway. The other thing is, as I said earlier on, is memory, and where do I spend my money on if I want to go and, spend space on the die? If I'm a service provider person, I want fast convergence and I want large routing tables. So I want really rapid updates. That's what Turles was referring to earlier on. So I want the memory on chip. If I put the memory on chip, I can't put other gates for forwarding on chip. So it might going to go and compromise on the bandwidth side or packet processing side, but I have all the memory on chip. You can argue then maybe I don't want that. Then I go off chip and put the memory off chip, but then I'm spending connectors that I could use for customer interfaces to go off chip to the memory. Again, a trade-off. And well, if somebody's asking me for, ideally I want memory at the speed of L1 cache for everything, but that doesn't exist, right? So the further you go away, the more you pay for going away. Problem. And then also I think, it's 2019 by now. Do we really need hierarchical queuing all the way we needed it 20 years ago? Because if my broadband home connection is 1 gig, I don't really care about that QS configuration on my router anymore. Because it just works, right? Do we need to go and build that really into the system again, spend gates on hierarchical scheduling? Well, maybe we can go design around that. The other thing is stats, and there's Ule, right? So a couple of key guys around vector packet processing, and that's just x86, sat together and said, we want better stats on VPP. And then, Ule chimed in, and Dave Barak, kind of the key guy for VPP, who invented the whole thing, chimed in and said, what should I go do? Should I go and collect stats, or do you want me to forward packets? I want both, no. So I can either spend a cycle on collecting something, or I'm spending cycles on forwarding something. And I think they came up with an architecture that allows for rapid collection of stats, but, there is a price that you pay. And the question is also, how often do you want to go and collect that? And in many systems, you can poll the system every, say, 1, 2, 3 seconds, but it's all the same because hardware only updates the counter every 30 seconds, and that's a trade-off. And what you see in core routing is we're doing that trade-off of you go fast, you have shitloads of table and memory, but you might compromise on the statistics that you gather. Because again, you can't have it all. If you want ultimate stats, then you might want to go and compromise somewhere else. And people build dedicated machinery to go and do top talkers and whatever. But again, we pay for that with either less memory on chip or less forwarding capacity. So there is trade-offs, and I just put some examples from classic SP, where we've been optimizing around FIB table sizes, stats, flexibility, QS buffering. So there is a shitload of memory on the chip arranged in eventually hierarchies. But we said, we don't deploy too many of these systems, so we're okay to go and maybe not go that optimal on power. Whereas in a data center environment on the right-hand side, it's all around power and bandwidth and speed. And these guys eventually don't even want large buffers, because large buffers mean delay. Do they have large routing tables? Eventually not. And what we see right now is kind of more people trying to play in the center of that, so that you can go and sell the same box to multiple people all at the same time and kind of, deal with that trade-off. But had earlier conversation today, which was exactly around that. And can we have it all? Yeah, it would be nice, but that's the spherical thing that we might not get, maybe from Spencer. John, I think you're going to go take us a little bit through why pipelines are difficult.
Yeah, so Yeah, here's the cartoon that I promised earlier about a pipeline forwarding architecture. And it's, you know, like I said, it's a cartoon. And the important piece of takeaway here is that when a packet comes in, some of it goes north and some of it goes south. And, you know, the two really only meet when you get to the output port. So you've got your first N bytes. They go up towards the forwarding complex. You've got the rest of, you know, your whole thing goes into your, you know, large pile of cheap RAM. You know, you buffer it towards your egress, and maybe you do another lookup on the egress, and it goes back out onto the wire. The header, those first N bytes get processed. You have you know, some large number of stages and potentially a large number of cores, each one of which has a large number of stages. When you're scheduling all these cores, it's really nice to be able to complete you know, the forwarding task in deterministic time, which means that doing looping and things like that is undesirable. And notably, when your headers get too big, that drives real cost, because you know, then you know you really are that all is L1 cache. And you know, if you tell me that I need to have twice as much L1 cache, well, Frank just talked about that. On the other hand, the data goes through RAM, which looks a lot like commodity RAM, and acts a lot like it too, and is slow like it too. So I think compared to 4 years ago when this was written, probably a lot more people are used to thinking about pipelines, because you can't turn around without, I mean, everybody, all of you have, like, you know, 16 cores that you're reading your email on right now, and you can't do anything unless you think about how to break a task down. So, you know, very much so in packet forwarding, what you want to do is you want to break down the forwarding task into a bunch of pipeline stages, each one of which ideally provides its output to the next one, and, you know, moves on to the next packet. And, you know, of course, you can make these things arbitrarily complex, but see previous discussion. Yeah, basically any time that you have to make a decision in one of these pipeline stages, or you don't know how many times you're going to have to recur, that has some, again, real cost at forwarding time.
John, to your point, right? So last one, if you have one label that can have multiple meanings, so you need to do another lookup. If you do that, reconsider that, right? So that's, I think, one of these things where you give these guys a really hard time.
Yeah, exactly right. Thanks. Okay, so yeah, things that are fully programmed are slow. Things that are fully set in silicon are fast. But yeah, this may pretty much reiterate previous slides. You want to talk to this one, Frank?
Well, I think it's an iteration of what we had before, right? So do we have to go and drill into that again? I think
no, it's okay.
I went over
I'm
that
glad to go past it.
Times.
Yeah, so I think this is worth spending a few minutes on, though, which is that typically there's a fixed header vocabulary. So, you know, at some point early on in the pipeline, you've got a thing that knows how to crack the header up into, you know, its fields. You know, so, and they're you know, built to existing protocols, of course. So protocols that you know, look like existing protocols are great as long as they sort of have semantics like existing protocols. mean, I think we come back to this again a little bit later. Yeah. So yeah, I think the only point I want to make to this one is that it's frustrating sometimes to, and I've been frustrated by being on the other end of this conversation, to say, oh, I've got this great idea of, you know, something that I can do in the forwarding plane, and to hear, oh, well, that won't work because your router foobar, you know, won't do it. And sometimes the answer is right. It's like, you know, take, you know, if router foobar can't do that, maybe it's time to take all of those, drag them to the dumpster, and replace them. You know, you idiot. But there's also this large category of things where it's like, no, that's the wrong answer, because either, you know, that wasn't a design error, that was a you know, informed trade-off, and you're going to find a lot more characteristics just like that in the market. And by the way, they're not going to go away, because if you want that, you know, limitation to go away, you want to be able to access, you know, infinitely deep into the packet. You're going to have to pay more than, or not you, but everybody else in the whole entire world is going to have to pay more than they turn out to be willing to pay. You know, that's, again, and when I say pay, I mean in terms of currency, of course, but I also mean in terms of, you know, power, heat, et cetera, et cetera, et cetera. Okay, so that's the sort of setup, and this is, Dan.
Before we go there, oh boy, this was a big dump, Dan Bogdanovich, by the way. And to be honest, I was thinking, and to say where should we start, it's one of the problems that we have is that our control plane are coming with restrictions because of our system architecture. If we could solve some stuff in the control plane, we would not need some of the characteristics in the hardware. For example, if you would have a good control plane that would be doing, you know, good traffic engineering, you don't need SD buffers. You can save that space, you know, for other functionalities instead of the buffers. So then the other part is how the vendors are organizing the packet forwarding in fixed ways where there are some flexibility, because it ties to their business models. That is another problem where they're not willing to reuse the same chipset. Give it to the developers that they can organize the tables dynamically based on the applications that you want to run. So you have the capability to size the memory in different, you know, in tables, inside the ASIC in different sizes that you need. But none of the vendors are really willing to expose that unless you're working directly with the ASIC vendor and you have the access to those APIs. So that would be also, you know, some of the things that could help you.
That sounds more like a business problem than an architecture problem.
Well, so it's a little bit of both, because they're restricting you because of the business problem, but you have a hard time pushing it through. Speaking from first-hand experience working for a major vendor. So that's, you know, that in the past. So that's a little bit, that also has to be looked into it.
I think some of the constraints still apply, right? So
I agree, there some of apply, but we could.
If you have an n stage pipeline and your processing requires n+1 stages, there's no way in hell we can fit that equally well. If you want to have a piece of the header that we pass along with the instruction through the pipeline.
I know, I agree with you. There are some trade-offs.
And you need more memory to pass through the pipeline, and we can't pass it through, then what do you do, right? It's a hardware constraint.
I agree. There are some certain where you cannot do more, but we could do more with what we have today when we didn't have some of those, which are mainly business restrictions imposed onto us. So on some of those.
Fair point.
Yeah. So that's and.
So I think you're saying that, like, not all smart people are the ones who are sitting inside the vendors and have access to, which is.
The VP will literally shut you down and saying no, because we cannot sell this. It will lower our revenue. It will literally come to that.
Florin Babuescu. May you quantify further your comment that the new protocol designs may heavily impact the cost of the hardware? I do agree in the context of the pipeline architecture design. However, for various other models in which your forwarding plane, it's a network processor based, together with some other elements around it, that may not be the case.
Yeah, I mean, part of what I've been trying to motivate here, though, is that those pipeline architectures are probably not going to go away because they're very cost effective. I mean, this is kind of the you're being cheap, no, I'm being realistic kind of argument. And I can only sell what people want to buy, and they buy what they need. And what they need in certain cases is, you know, if you go back to Frank's, you know, cool circles, you know, is sometimes, you know, density, speed, and BTUs.
But I think to your point, so the pipelines are just one example of multi-stage. And there are certain constraints that apply to pipelines that might not apply to other multi-stage architectures. Like if you have multi-stage with run to completion, you don't necessarily need to pass memory around with the individual steps. So there is trade-offs among that. I think we picked one example, forwarding architecture, because it's quite well used across the industry. And maybe I think from a considerations perspective, most of them still apply. Maybe we'd go through the considerations and then
then we can come back to continue.
At the very end. Would that make sense? Because I think there is some stuff that you want to go and implicitly raise here, what I'm feeling, that is in the next slides that John has.
Yeah, that sounds fine. I mean, I guess we'll take your thing also, of course, Carlos, but I want to just jump in and say, you know, to some extent, what I'm trying to, you know, at least from my point of view, trying to describe is like a bottleneck. And, you know, it's useful to analyze bottlenecks, and you guys can fight over who talks next.
Actually, what I wanted to get to is that despite a multitude of protocols that may be needed to be implemented onto the forwarding plane, the basic elements that need to be executed are quite clear. And based on my experience on at least 3 different designs at 3 different major network equipment vendors. So from this perspective, I mean, you're basically going to have a search and an action. And how the search it is, practically how deterministic you may be able to do it in a certain memory bounds, it's important. If you go further to more fancy type of searches, then when several issues are coming. And the discussion is also very particular per architecture type design.
Right. Now I think that we're in violent agreement.
I wanted to get back to the point from Dan about, you know, exposing lower layers of the platform. So I mean, the lower layer of the platform you're exposing, the more expensive it becomes to support that, right? So that's basically, I think, one of the reasons why, you know, there have been various attempts of APIs and other in the past. You know, how do you consume it, right? Most customers really come with requirements of functionality at a higher layer. And, you know, that's why I was thinking that the programmability, like, you know, some programming language, P4, whatever it would be, ultimately gives you another way as a customer to approach the vendors, right? It's not specific to a particular vendor's chip itself, but you can go and say, this is what I want to run. Show me that it does, I don't know, 400 million packets, you know, whatever performance you need, and that goes across the vendors. And that's at least, you know, another stage of engaging with the vendor by being able to do that.
If you go back to your, to Frank's, it was back this one. So you have the SP style and the DC style. And what I'm trying to say is that in the ASIC, you have memory and it's being laid out in fixed tables, you know, that are using that memory on the ASIC. If you would have better control of those table layouts, that you can dynamically change it, you know, based on the application, you would have, you know, like less of a trade-offs in there. And I would even say that you could remove some of the buffers if you had a better control plane, which would when you remove the restrictions of the router system architecture that you have described at the very beginning. So some of the vendors, ASIC vendors, are trying to give you more flexibility in that way, how you can lay out in order to get some of the better the trade-offs, where some of the but it's very hard to get to that layer. And when you are talking as a protocol designer, what you're trying to do, you are seeing you're getting hit by those restrictions.
Yeah. I mean, in the existing model where you're only coming, with solution requirements, it's basically that the product already has to be in the different market spaces, and then the vendor will figure out how to reconfigure it accordingly. But other than that, I think it's going to be very hard.
So if I could just do a chair interrupt for a second. So basically, we are to slide number 30, and we're kind of hoping to talk about things to keep in mind when designing a new protocol. I think we are kind of assuming that people will continue to improve routing and continue to improve routers, but we also wanted to talk about what people are supposed to be doing in the meantime, and that includes people that are not working on routers. So, like I say, I'd like to let you folks finish up your presentation probably in the next 20 or 30 minutes. Does that seem about right? And then the other thing was, of course, this is a working session, not a watching session. So that's our opportunity to go crazy when that's over.
Thanks. Yeah, and we're kind of in the home stretch of this deck. So this is hopefully... Okay, first of all, this is I'm 100% sure not a complete list, but it's trying to take actually some of the one of the earlier questions or comments rather was there are certain universal truths that people who have done this a bunch of times have observed, and this is kind of trying to distill them down and present them as a set of almost aphorisms.
And John, I think this is a very valid discussion that we have right now with extension headers and using them extensively, like what we do with, say, for instance, IOM. So depending on what you have, how deep can you parse, what information goes where, can my header go first, please, so that I can parse it because I don't care about your header. So I think that's a very valid discussion. The other thing is, that's the parsing part, right? And we're very aware of that there's limits, and people have been pushing these limits pretty far out. So there's been, if we go a couple of years back, people were able to parse a couple of 100 bytes into the packet. People have not been using that capacity at that point because extension headers didn't take off the way we were thinking they were taken off. And then people were suddenly pulling back again from a parsability perspective. So that also happens if certain things don't get where they get implemented, but they don't get used. I think that's also something that we see as a dynamic because vendors react to what's been built and what's been used. And the other field is like 128 bits are really a challenge. So if we would be able to do lookups on less, and if you design new things that use less bits, that would be good, right?
Yeah, and I think sort of also a higher order point, that is kind of what you were saying as well, is O of 1 is way easier than O of n. I to some extent don't care what the constant factor is, but O of n is really a pain. So let's see. Is this largely what we said already? I think it is. Yep, I think this is, again, this is just saying headers that can be composed in arbitrary order is quite painful, especially for certain architectures that have a fixed order of of units. So don't do that. Inventing new kinds of headers. If you invent a key that looks just like a key in a different kind of header and it has kind of sort of similar semantics, so I can rejigger my lookup unit to do a slightly different kind of lookup, but it's still a lookup on a thing that looks about the same, that's probably fine. Taking a header layout and saying, oh, I can abuse this in a new way because it has the right number of bits, but I'm by the way, going to change the semantics in some non-trivial way, is you're not necessarily going to be able to reuse your existing hardware. Also, recycling packets sucks, which is the last bullet there. This says flow identification, so don't panic. What we're talking about there is entropy identification. And unfortunately, we have done a terrible job at this and continue to not do a terrific job. But it would be really nice to do a better job at this in the future and to put entropy at a fixed offset from the beginning of the header. I don't really care what the offset is, but if it could be fixed, please, and if I wouldn't have to go and like look at some field and then it says keep looking down and then I keep looking down, and anyway, you get the point.
Or even more so, design something that doesn't require flows. Much better. If you can go deal with packet reordering and all that stuff at application level, then, well, nobody would need to go and deal with flow identification in the hardware.
Applications and transports, please fix this for us.
And makes it much simpler, right? We don't need all that crazy stuff that we do for ECMP today. We could just do packet by packet, count round robin, easy. That makes it really hard because it requires us to go and do all kinds of shitty parsing.
Right. If we had one thing to go back and do differently from starting from the 70s, I bet it would be that.
Eliminate flows day one.
Tom Herbert. So flow label in IPv6 is not sufficient?
What do you use the flow label for again? Could you tell me?
To identify flows for ECMP. We have it. It's there. It was expressly designed for this purpose. As far as I know, it's not. It's being set on the internet now. Is it being used by these routers? And it gives you exactly the properties you want. It's at a fixed location, easy to process. It's always in the IPv6 header. Most OSs that I know of, Windows, Linux, iOS, will set it. Well,
so Stuart's comment, Stuart, if you could come to the mic, if you want to join the conversation, that would be great.
So the question was, is it always set? And I would point out, even if it's not set, you still have the IP addresses. So ECMP is an optimization, not a requirement from that point of view.
Did you just say ECMP is an optimization, not a requirement?
That's not what we hear. That's not what we hear in designing routers.
Okay, yeah, no, that's really not true.
And if you can't trust a field, you can't use it for something as important as this.
Okay, but you can't trust any fields by definition, other than the IP header. If you're trying to go down into transport layer, you can't trust those either.
No, well, you know what the IP type is, you know what the follow-on type is, and you know where the ports are, and that's what people have been using for many, many years.
And it's an ongoing problem. I mean, it's not perfect, but
well, okay. So
we're highly motivated to get as close to perfect as we can.
So we just talked about header size. So now if I have to go down and find transport headers, something has to give here. Like Frank said, you can't have everything. So I can't have an easy way to identify flows and yet short parsing buffers. So there's got to be a trade-off somewhere.
Right, but ECMP is not a nice to have.
Okay, Parviz Yagani, Huawei. Great background and the history of the routing, and there is a paradigm shift in the industry. I'm not clear if you can really spend a few minutes to see how that would really impact the future of IETF and the protocol machinery of IETF. It seems to me...
Okay, you know what? So I would like to encourage you to hold that question for a few more slides.
Okay.
I am not going to talk about, sort of future vision for the next few slides because I'd like to wrap this as Spencer requested.
Spencer wants that discussion at the end.
Okay.
Yeah, this is the discussion I think that Spencer is asking for, but we're trying to get there.
Wolfgang Beck. With regard to packet reordering, it's not that long ago that I had a heated discussion with a vendor who sold us a carrier-grade system where you had to choose between selective acknowledgement in TCP and the ability to process reordered packets. So,
and just to make sure that I'm doing the right thing for everybody in the room, I'm hoping that the discussion starts at the end of the session. If we can solve all the problems of routers and the way and forwarding and protocol interactions in this room by 5 o'clock, that would be awesome. But just in case we don't, I also want to be talking with you all about how we can continue that discussion.
Elman Kirchner. Just on the last point, ideally, yes, flow identification and packet fragment reordering from a chip perspective would be ideal. However, if you look at the real end-to-end thing, I mean, there are security considerations and, stateful firewalls and so on. So if chips drop that feature, others will have problems. So we can't optimize for chip level and forget that, we are trying to do end-to-end stuff.
Right? No, remember at the beginning I said that everybody else has to do cheap, fast, and good? No, I'm joking.
Exactly.
It's a very good point.
We would have everything for us. It would just defeat the purpose.
It's a great point.
So there's a huge elephant you haven't got to, which I hope you're going to get to, which is per packet state. Is that in your slide deck?
I don't think I do have something on that. Let me just fly through the next things, and then we can sort of open it up for, be sure that we've checked off all our boxes, no pun intended. Checksums are expensive. Don't use them just for fun. Don't invent new ones just for fun. This is not actually what Stuart was asking about, I don't think. I think Stuart was, I believe that you were bringing up the point of you can have state in the forwarding plane or you can have state in the header.
Yeah, I mean, the thing that was really a problem was people coming to DetNet expecting we could do per packet sequence number checking and those sorts of things. And you discover that actually it's really hard.
Okay, that is kind of what this is going on about then, which is that, sort of traffic-driven state is, has been proven not to work out well.
That's why we wanted to talk.
Stop, right? I think we had this wonderful contentious slide up there.
Sorry, this one?
Yeah.
Okay.
So
here, you
minimize
walk
the
around
state
a
up there. And, I think one, again, I hate to say that because I love multicast, but from a hardware perspective, it's a load of effort. And people put dedicated replication engines. It makes the chip much more complex. And so I think how much replication you need, consider that. How much replication we want at a particular point in time, consider that. So it is a real trade-off that people have to go and make, which is why if you look back, loads of people were blaming certain devices not to do proper multicast. Yeah, it was a design decision, right? And they traded unicast capability or maybe sometimes cost plus unicast for the multicast thing. So I think that's some of the background that happens there. And if you feel forward to one more, I think that's the wrap-up thing, right? That we want to go do jointly. So not everything can be done. Can I just 2 more sentences and then I think it's free format anyway. We can't do everything at no cost. The other thing is, and I think that's something that we might want to go inspire as a discussion topic is, should we, when writing a draft and completing the draft, have some of these considerations that people think what their protocol should go do and what some of the assumptions are, should that be documented in the document and written down so that some of these things are not implicit but explicit. So I assume that I can parse packets up to, say, 200, 300 bytes deep. I can do this, I can do that. Should we go and document that? I think there is a problem with certain things are designed for a particular domain. And it might well be that today this domain exists. Tomorrow, we don't know the future. So it could well be that this domain becomes something else. It could become the big I internet, or it can just kind of fall flat on its face. But I think what is niche today doesn't need to be niche tomorrow. But at least I think articulating the requirements that you have in mind for certain things, from my perspective, would make sense so that loads of these implicit assumptions are put on the table, especially when it comes to what the forwarding capacity should be all about. And I think that's one of the discussions that when we did the prep calls with Spencer, Alvaro, and team, that they wanted to go see Surface, which is why we put it here. And now it's all yours. Sorry for that.
So thank you. I'm lucky to be the first one now in the queue. Going back to your previous slide, regarding with keeping state information, that again, it is a matter of, and it is architecture dependent. There are certain architecture already out for more than 10 years, for which this is not an issue. I would have been happy to see other elements being included, like search types that you may have it. These are directly impending practically your design, no matter what type of architecture you do have. So something like practically favor hashing or favor exact match, favor prefix matching versus generic packet classification, and so and so. I mean, unfortunately, after staying in this presentation, it's like I slept for 15 years, and I could have come up with the same type of discussion 15 years ago. There is nothing
Correct.
changed.
And the deck was started in 2015, I think, yeah. Well, loads of this is motherhood and apple pie, and they just wanted to go and cook that up again. So I think that's a good point. What we could do as a follow-up is maybe just focus something just on lookup in the next go-around.
David Black,
Because that warrant an entire kind of discussion.
the sliding headers and tunnels flew by way too fast. We have increasing amounts of tunnel and cap protocols in the IETF and increasing design expectations that NCAP, DCAP, and cross-header processing on DCAP will occur at line speed. Would you care to comment on what to do and what not to do in this space? You lost that one once, Dino.
I think it's very generic, right? I mean, I think we're looking in the cases where we feel it's worst and how much we can optimize it, and we think we can live with the optimization, right? So if you have an ongoing chain of DCAP and NCAP with the same thing, obviously you can optimize that quite well. But because even the length doesn't change, you just need to figure out if you can flatten the processing to actually recognize that situation. So, but yeah, in general, all these encapsulations are typically very expensive, and typically they either cost more gates or they cost performance because you're doing things like recirculation.
Dan Bogdanovic, one thing which I find would be useful in general for the protocol designers is to put in a document with do's and don'ts, what is beneficial, what is not beneficial when you're doing a protocol design. We can talk about system architectures, what we have the problems, but if you would have layout what are your restrictions and what would be the recommendations from the hardware perspective for certain protocol adoption to be faster, that would be very helpful, because we can try to optimize the thing that we have as much as possible, but if you're adding a new header that requires new parsing and you want to do it fast, as you mentioned, you will have to wait a couple of years until that being put into the,
But I think the answer is it
silicon.
depends, right? So I'd rather have spelled out what you want or the assumptions that you have, as opposed to there is some generic rules from a hardware perspective. I think there are none. You can design the hardware around your needs, and then your additional header I can slap on without any effort. It just depends on what the underlying system is built towards. And I think that's why I do believe that something that spells out the assumptions or requirements is much better than having something that, talks to spherical routers.
But what about you knowing what is possible today versus what will be in 3 years?
So I should probably say something just for a second here. So I think that we're talking about, I think you had a perfect question for the next little section, which is where I'm hoping we're going to talk about is not how to solve specific problems like that. Solutions to specific problems that have been named here, but how we solve, those problems or keep them from happening going forward. When you're asking about, are there recommendations that we can make so that people will quit tripping over their own shoelaces? I think that's a conversation I really want to have with the room. So I'd like to and we can drain the queue and everything if you guys talk fast, but I'd like to give these guys a chance to finish up their section and then turn over to the room for us to figure out what next steps look like. I think, are we good with that? Cool.
You know, we are focusing on a box called router. We want to make this box look really nicer, bigger, faster. That's not the point. The point is you have to look at the bigger picture. Like Frank already mentioned, that telemetry is a part of it. It's not only packet forwarding. Packet forwarding is only a small piece of it. Okay? So that is where, Spencer, when we have time, I guess, John, you said we are going to talk about that. We are making this box, which is a router, look better, faster, or John, you put it very nicely, more efficient. That's only a small piece of the puzzle.
I have a few points on the slides we just went through. Should I wait or should I go through them? Okay, I guess silence is good, so agreement. All right, so in the slide 31, this is Rajiv, by the way. So slide 31 said, parsing 48 or 32 or 64, that's great, but 128-bit, did we forget to send the memo to the ASIC folks that IPv6 addresses are actually 128 bits? That has been so for the last 20 years or so.
But wait a second, just because the IETF has decided that the internet should do this, doesn't mean that a chip designer has to like it, right?
No, of course not. But that's been parsing 128 bits. So it seems like we're still rooted in IPv for lingo from 30 to 64 bits. So is there still a merit in having to restrict? I mean, and granted, I get that we can't just keep parsing hundreds and hundreds and hundreds of bytes in a packet for obvious reasons. But there has to be at least a guideline. What's optimally minimal, right, as we go along the timeline? Okay, so second point, now I'm thinking about this, and then slide 37, we're saying, wait, keeping state or not keeping state on slide 37 in the forwarding node is better. Well, but that means keeping state somewhere else. So mostly nowadays that's in the packet. But if you are keeping state in the packet, that means you're putting more information or highlighting the need to parse that packet a bit more intelligently, which takes us back to the problem of parsing. So I'm scratching my head on that. And the last one, and I'll pause, is degrading multicast to unicast. I think what we're really saying, degrading the ability to be replicating, that is part of multicast, but nowadays we also do that with unicast. So am I correct to understand that when we're saying degrading multicast, we're really saying, well, degrade having to replicate the packets on the box? Maybe I'm not getting that right, but at least the statement is making me scratch my head.
This is all from the perspective of keeping hardware simple, right? Obviously, that's one end of the side, and obviously, I think we would all agree we don't want a network where we don't have IPv6. So sorry, chip designer, you have the pain there, right? But basically, ongoing, we should still consider these, poor chip design effects into account, right?
So before we keep going, just a time check.
Yep.
We have this room till 5. We all need to go to the plenary. Well, at least we need to go to the plenary at 5:10. So after the discussion, we still want to go through a couple more slides so that we can talk about what are the next steps.
There are also 3 more slides that I wanted to present.
Right, okay. Yep. So we want to leave enough time for that. It's 4:23 on my watch. So I would like to finish the extra slides so that we can have the discussion about what are the next steps. Maybe starting 25 minutes before 5, so we can have time for that, can go to the bathroom and all that stuff. Okay?
So
Yes, thank you.
I should just make a small announcement. We've just published RFC 8507, which gives you 64-bit addresses for that protocol.
Okay.
It's meant as a joke, though, if you didn't get it. But go and read RFC 8507. I would love to. That was the intention, right? You guys, or someone, not you, Dino. We got to relay.
Ben Kaduk. So there were a couple of people talking about whether it is a good idea to try and document some of these things. I think the answer is clearly yes. Whether that ends up being an RFC or BCP or just a wiki page, I don't know that I have a strong preference on, but I think it's really great if we can be clear about what behavior is good for routers and also what behavior protocols are sort of expecting from their routers. So if we talk about what we do and what we expect, then we can figure out if those match up, and if not, what we could change.
And maybe that's a discussion for the end in terms of how and what could we do as a follow-up from this, as Spencer said, right?
Yeah, definitely. And I have one other point. So there's a slide that was talking about how avoiding flow identification and being able to accept packet and fragment reordering would help the hardware. And I guess my question was sort of who would need to coordinate to make that a reality? I mean, we have people that are designing quick, and they're saying, we don't need our packets to arrive in order, and we can build into quick what we do to reorder that. But then we have people coming up and say, well, I have my stateful firewall, and that would not be so good if the stateful firewall is seeing things out of order. And like, are there other things on path that need to look at this? I don't have a great picture of who would need to, like, how many people would need to change in order to make that happen, that we can tolerate the reordering.
Hi, Tony Lee, some router vendor, one of many. I'd like to respond to the comment about 128 bits. After being there, we did take the comment about 128 bits to the ASIC folks, and they came back with a different comment, which was, no, 128 bits are bad. And the IETF chose not to listen. Okay? We specifically asked for variable length addresses, and the IETF said, no, blank, blank. Okay, if you're not going to listen to the ASIC folks, then don't expect the ASIC folks to listen to you.
Jeff, so, a lot of us have been doing this stuff for 20 plus years, so we should learn. There are kind of rules of thumb. You want to build it well, you want to design it well, you respect layer boundaries, you decouple reachability from policies. And we are going like a pendulum. It reminds discussion about fully centralized versus fully distributed. We decide, let's put all the state in the control plane, we build our CPT, and then, hey, soft state kills our control plane, let's remove all the state, and then we build number of technology we're building now, right? And suddenly, oh gosh, anything that required state in the network doesn't work, multicast doesn't work. Let's go back and can we find something in the middle by cooperating that actually does work? There are very good examples of things that work really well. LTVPNs, beautiful, right? So they did work, they do work, and so there are good precedents of finding right balance between what goes into control plane versus what's going into forwarding. And we should learn on our mistakes and things that we did well.
Can I maybe cut the line after Dino? So then just show 3 more slides, and maybe that expands the discussion a bit more, and then we can back.
So, Stuart, Brian, various people have suggested that we write down basically a forwarding specification or a specification for how this works. Well, my first IETF was IETF 16 in 1990, and I went there because we were just starting to work on the rewrite of router requirements. No one has ever successfully written that down. The world is orders of magnitude more complex. The optimizations and the economics are orders of magnitude more complex. All we can do is to do some tutorial, but never more than tutorial.
I have a general comment, which is a little bit beyond just about the packet forwarding. One thing that's very kind of strange to me coming to this meeting was I was expecting something to tell me how we're going to do forwarding in the future and how we're going to get things better. I understand that we want to have simplicity, and I understand we want to have performance, but it seems strange to me that we are asked to bend over backwards to fit the hardware. I think the hardware should go where we want it to go, not the other way around.
So the whole point of this talk.
Yeah, I agree.
So to repeat Stuart's comment.
I agree, but it's not only that. We've been talking about trade-offs, but then we're erring over simplicity about what we should be done.
Stuart, could we first and get back later? Thank you.
Tony Lee, Arista. Would one of you care to comment about SRv6?
This is Dino. Kind of an idealistic comment. The original internet architecture was supposed to make hosts robust and more complex than the inner network. Routers were supposed to move packets fast and do nothing else. That's the way we started building router companies. But turns out router companies didn't want to be commoditized, so they had to put additional features in. Do you realize most of the real estate on any die on any router is a huge TCAM for access list? The access list table is larger than the fib table. What the hell are we doing? Why in the middle of the network we have to check if a packet should be dropped or forwarded based on policy? Shouldn't that be done in the control plane? Shouldn't that be done on the edge? So the problem is, if you guys want to build fast routers and make these hard trade-offs, you have to can't keep changing the problem set. If you want to keep changing the problem set, build a general purpose programmable forwarding engine. But if you want to build a super high ASIC, you can't keep changing or predicting what the future is going to be, because then it's going to take 5 years to build this new functionality.
Sorry, I was just cutting the line just to throw in 3 more slides to hopefully actually also relate a little bit more to what the discussion started to be about. I think we learned life as a chip designer is miserable, and the last part was reflecting back a little bit to, please take a little bit of that pain as a protocol designer. Now, I wanted to basically try to create some more insight into that connection between the forwarding plane and what we're doing at the IETF. One interpretation of the next slide, I'm going to give one example. The simple interpretation, obviously it couldn't work and it had to be painful because it was multicast, like was said on the last slide. My perspective is actually a little bit different. It was basically a perfect combination of, bad code and bad IETF specs that basically was not taking into account, the need to document forwarding plane problems in a way that really they, must be implemented correctly. And this is basically my story from the beginning of 2000s when we were using the router alert mechanism. Anybody who doesn't know what router alert is, please leave the room. No? Oh, okay, fine. So what we did was a reliable multicast protocol called PGM. And basically that was using router assist in message and signaling packets to basically let the router help the end-to-end communication of the transport protocol by imploding NACs or caching and retransmitting packets. You could say it's similar to ICN just a decade earlier. But be that as it may, that was in our opinion, a perfectly well-working solution. Unfortunately, when we started to deploy it in customer networks, what happened was that these router alert packets were perfectly proceded by the routers in the network that understood PGM as they should, and they were designed to have the performance needed. Unfortunately, also a lot of other routers that had never heard the word PGM in their code at all were also punting these packets because, well, it's obviously a router alert packet, so let me punt this to the, aforementioned, remember my first slide, Atom CPU, that can just maybe software forward, let's say, 1,000 packets as opposed to 500,000 as the ASIC at that point in time. And yeah, obviously they got completely overloaded and killed because the only thing they were doing is looking at the packet and saying, what? Router alert? Next protocol PGM? What the heck is that? I have no idea. Simply let's forward it in software. And so what happened was that the specifications that we have in the IETF we're basically not making it clear that you really, to get workable router alert, you must only punt the packets that are of interest to you. And that's not just any router alert packet, but it's basically the packets of protocols. Next protocol, there's also a particular value field that could have different content, the combinations that you're going to do something with it, in your software control plane, forwarding plane, however you want to call it, and everything else just continue to forward in hardware. Would that additional differentiator to, send packets from the hardware forwarding plane to the software forwarding plane been possible on all platforms in 2000? I don't know. Definitely on a lot of platforms where it failed to do so. But today, obviously, it's a total no-go. But still, we don't have RFCs that mandate this level of requirement against the behavior of a functionality, because in general, my perception is, we're not about to specify internal of the nodes, so we're always trying to wiggle our way around it. I was giving here in italic one way on how I could try to wiggle myself around it, but obviously it would be a lot easier if we had more freedom in even normative RFCs to make specific, requirements that today we might consider to be internal only, even though, I think it's very nicely externally be visible that, your packet throughput went from 500,000 per second to 1,000 per second, right? That is externally visible, right? So this is basically my example slide of, it's not only a problem of the hardware, but there is also the problem of bad code and bad IETF specifications.
So I'm going to jump in for just a second, Torles, and say that I think what I hear you saying is that we have for a long time had a religion of like, we're not going to mandate architecture, it's not our business.
Right.
So, and, sort of, we earlier had Dan saying almost the opposite of saying, just give me the cookbook and tell me how to fit into your, architecture and I'll do it.
Yeah, but not in normative protocols that we do today.
And I think that, and Frank said something a little bit different again, and I think what I'm hearing is we sort of need to, lose a little bit of the religion, and we still should not be mandating architecture, but maybe it's okay to acknowledge that architecture exists.
Yeah. Let me go to two more slides because, Alvaro was just giving me a time limit, so that we're at least through the slides. So basically, I wanted to give two counterpoints, right? The one counterpoint is exactly through the need for speed in the forwarding plane that we see a trend of simpler fast path and control plane, right? So basically slow path, all these difficult packets, and then we're going forward and saying, please let us have less difficult packets that we can't process in the fast path, because, the slow path, something punting it up to control plane CPU processing it, is becoming ever more so useless, like it's completely useless, let's say, in data center switches. And, I think in our evolution, we've seen, hop by hop headers, fragmentation, reassembly, we've been trying to push back on that. It's actually not only packets that by themselves need to be software forwarded if the hardware can't do it, but it's also what, at least in the IP multicast world, we've come to call data-triggered events, which is basically things happening in the forwarding plane, like special packets that I don't need to see in the control plane, but where I need to get event notifications to do control plane actions. And so we've basically, I've given some more example there. In multicast, we worked something like 15 years on evolving from something that, as I initially said, was implemented on a Sun workstation of a researcher, built the M-bone, up to basically, our last protocols like BIDIR PIM that wasn't having any data-triggered events anymore, just to fit the protocol evolution perfectly with the requirements of hardware, and, allowing us to work in the smallest possible CPU. But quite frankly, we're glad that we did it from the business perspective, but definitely it doesn't necessarily result in the best user operable protocols, right? So we basically were doing compromises for what we ultimately set out to achieve initially, obviously way beyond what we can talk about here. So how about intelligent fast path, right? Because I think as people who built this hardware, we don't only want to basically give you the fastest, least intelligent hardware, but we're always looking for things where the hardware intelligence can add value to the solutions. And, I think there's a lot more things we can do with the latest generations of NPUs. And so what I mentioned, these two topics of, the IOM, I think that's fairly well known. We also have a draft for where we basically put into NPU in our prototypes for basically a lightweight equivalent of RSVP to basically establish forwarding state at the speed of NPU as opposed to at the speed of control plane. And that actually is a totally different protocol design, because when you look at it, you need to change the protocol to be lightweight enough to be processed by the NPU, similar to the the IOM stuff, where you can't have a lot of acknowledgement exchanges or so. So protocols might actually start running in accelerated forwarding plane. Maybe it takes a decade or so. We don't know, right? So how do we deal with the conflict of on the one hand side, we heard 90 minutes about make it simpler so that it can be cheap and fast. On the other hand, how do we open up the opportunity to explore more intelligent forwarding planes and leverage their speed and flexibility? The last point, maybe, there was a really nice, research project that I saw from Berkeley 2 years ago, and they were actually looking at exactly what we always fear to be really bad. So let's say MAC learning in 802.1 in bridging, right? Totally always data triggered events, data packets come along, you learn addressing from it, right? And there we're taking it forward and saying, hey, we can do this in NPU now. They program prototype in P4, right? Basically, if you can do it now in hardware and it works at line rate speed, it's really a great simplification of things. So we'll really need to find to counter, these two sides of the equation of how we deal with forwarding plane. So line is open again for everything. Whole side, I think.
Reverse it?
No, sorry.
Okay.
Hang on a second. So we're going back to other presentation. So this is where we were when we came into the room this morning, this afternoon, which is basically the chairs and Warren talking with people around here that we had, kind of here's problems that we know we've tripped on. And then from Frank and John and Torles, we said, oh, here's more guidance, here's guidance that we are getting. We did ask Bill Finner, where he thought the problems were, and he said basically anything we did in the 1990s is going to be a problem, which I thought was hilarious enough to put on the slide by itself. But you can kind of see where this is sitting right now. Next slide, please. So if we're looking at kind of the summary of implications we're headed for, and next slide, please. We could do a lot of things. I guess I should ask first, does anybody in here want to work on this more? Could you come? Cool. So, my question was basically, we could publish minutes from this session and thank everyone because we've solved all the problems. We could publish informational report from this session. We could request a mailing list to continue discussion. We could charter work on recommendations or BCPs. I saw Benjamin mention the wiki for this kind of thing. Can we talk to operator groups to level set on expectations? And I'm very interested in hearing other suggestions from you all.
This is Dino. I just want to make 2 points about multicast in going in reverse order. The data-driven events thing, Torles, you were there, so you know the history. It turns out we wanted to signal sources in the network by using a control plane, and this is to Tony Lee's point. We asked the IETF to have a request to send message, and it was not in the current way the multicast service model was defined, so it was said no. But we actually did get something out of it that we could have used. We could have hacked up because there was this thing called the RSVP path message, because we needed to signal from the source to do reservations, but not to do multicast state. So interesting change of events there. And then the one slide, there was a reference to multicast needs to be degraded to unicast. It turns out if you're a FIB programmer, the hardest thing to do is to program 18 line cards and make them in sync in the shortest amount of time. You need multicast on your switch fabric, or there's no way you can scale that. Now, I know that's different than multicast replication on the network, but if you're going to put it in your switch fabric, you already have most of the hard work done on your internal switch fabric.
Dan, I agree with Dino's comment on multicast. And one of the things is also is a replication to Dino's mentioning that Today, we have more space on an ASIC for ACLs than we have for forwarding. And this is coming from our bad network management practices. Many of the network management issues that could be solved in a different way, we are trying to solve in protocols, which are then impacting, essentially our ASIC designs. There's really no need for the operator to say, oh, if ACL is in there, it should be never deleted, and it just grows and grows and grows. And they just put it indiscriminately across the network and many different nodes because it says it's better that it's there than it's not that it's there. And that is a lack of network management tools.
I mean, this is so ridiculous. I don't want Dean to talk to me, so we have to install an ACL in a router in Japan. And by the way, we're doing that because Dean might roam to Japan, so that router needs it just in case. How well do we do roaming on the internet?
Okay, I guess Parviz Yagani, my earlier question is the vision of IETF, and if the life goes on in IETF using the old mindset. Today, if you really look at the application layer networking infrastructure, the framework is widely known and deployed, is being deployed. So there is a vision there that the actual function, which reflects the reality of a business value, in this case for IETF, the business value is how fast you can move packets, yeah? How fast you can move packets. So that's when you move from a PNF, PNF is like a physical box today, or VNF, the NFC term VNF, and now we have CNF, which is containerized network function. In the world of CNFs, you don't have to deal with PNF issues. This is my view, learning from the routing, switching, coming to NFV, and now we are talking about CNFs. My question for IETF is, okay, if the application layer networking infrastructure is well designed, well established, and it's been deployed, we can basically use the same concept and apply it to layer 2 and 3 and layer 1, the networking. Why not? We can indeed take the core function, which is packet forwarding, and then we take everything else is not packet forwarding. It doesn't have to be SDN, like centralized controller. You can have that distributed, well-distributed functionality of something like Envoy in a context of like service mesh. As a matter of fact, I don't know if Ed is here or not, there is an effort going on in industry that how you take the IETF protocols as tools and apply it to this new concept. I want the people that were talking, like Frank and John and Thomas, to talk about this, how that would impact the future of IETF, not necessarily from a routing perspective, the overall IETF protocol machinery and how that's going to go to the next, perhaps this serve this purpose of the industry for the next decade or so.
So another elephant, and I think there may be a reference to that in the previous comments, Stuart Bryant, is people want to do virtualization down at these sorts of layers and do the sort of things that we do in the sort of virtual moving applications around. Well, I'd remind people that holographic networking is currently expected to need a terabit per second per user. And if you don't get the latency way, way, way down, the user feels sick. So, we can't do some of the future applications unless we have simple, cheap, fast, effective, highly optimized forwarding, and that cannot be done with some of the features that people sometimes think are easy to add.
I should mention that we have about 2 more minutes in this session, so if you, the last two guys at the line could be quick, that would be awesome.
David Black, sure, I got to try to say some of the questions on your side, on the slide, Spencer. So I'm from transport. I don't work directly on routing, but I use and I'd like to believe that the protocol design work I do has some cognizance of what it takes to make routing effective. So I'm very interested in the output of this session, and I'd encourage to go beyond the what was said minutes to an informational report summing up things the rest of us can use. BCPs would be wonderful. I'm not holding my breath. If you want a mailing list, that's nice. I don't expect to sign up because I want to see the output. I don't care. I don't care to be one of those who makes the sausage. So there's some quick stuff to chew on.
Tom Herbert. So on one of the earlier slides, there was a really nice taxonomy of various routers, and they were everything from IoT devices to high-end. I think somewhere in the later slides, we were more skewed towards high-end when we start talking about header lengths, even checksum. The problem that we face, and David might have alluded to this, as a transport protocol designer, if we want something to work in the general purpose internet, we have to design for the least common denominator. So what is the least common denominator of all those? And that really pushed us down to how much functionality and evolution we can have. So a way forward really has to be that least common denominator problem has to be attacked, I would say.
If you want to, across the middle, it's micro package, the tiniest packet you can have, the fewest fields, zero state, and that's what you have to design for. Everything else we put in there because people didn't allow us to do that.
Well, but that achieves at least common denominator, and that does not get us forward motion in the internet. We would be stuck with IPv4 still if we didn't have the ability.
So just maybe to get back to David's stuff, right? I mean, we were very centric on forwarding, and basically, the QS things in the hardware that, relate to the transport functions, you just add a 0 to any time that you have how long it takes to get things done over in the forwarding plane, because that's our experience, how long it takes to get AQM or ECN or any of these other QS things into a network as soon as you get out of CPU space.
Okay. I'd like to thank everybody for coming, and I'd like to thank especially Frank and John and Torlis for putting together the information that they put together for this, and thank my co-chairs. We are going to have a survey on this, and we need to adjust a couple of the questions on it, so it will be right tomorrow. But we'll drop a note to the IETF 104 attendee list, and we'll let you know when it's time to jump on that. But thank you all for being here, and I'm going to turn over to our area director.
And yeah, one quick question just as people are leaving. So this was sort of the first in a deep dive series, or proposed sort of deep dive series of topics. And when people are filling in the survey, I think it would be useful for people to sort of keep in mind if this format or the sort of take a topic and investigate it in depth is something that's useful. And when you're filling in the survey, sort of try and answer that and figure out if more things like this would be useful. And are you going to ask me what topics they might be?
Can I request it scheduled in open time so that all areas can attend? And that was one of the really good things about today.
Yeah, there's going to be much discussion on scheduling, I suspect. Thanks, everyone.
Thank you both for extremely your help with this. It was great having you here. That's on the list of things that I would never try.
But actually, it's not that it doesn't work.
I think we're all